The Australian Research Council Centre of Excellence for Climate Extremes is an international research consortium of 5 Australian universities and a network of outstanding national and international partner organisations, all supported by the Australian Research Council. The Attribution and Risk Research Program, led by Professor Lisa Alexander and Professor Julie R. Blaster, is one of 5 key research areas within the centre.
It's clear that human-caused climate change is already influencing damaging climate extremes and will continue to do so. That's why our attribution and risk researchers seek to understand changes in climate extremes, such as heat waves, extreme rainfall, and droughts, and what has caused these changes.
To understand what causes these changes and to best assess future risks, our research programme has 3 overarching aims. They are to better understand the processes that cause these extreme events, to improve the climate models that simulate these events, and to improve how we use observations in climate models to understand the likelihood of future extreme events. It involves complex physical science and modern machine learning techniques, but its outcomes will directly impact the policies and decisions that will affect our response to climate change.
With this information, we can help countries, industries, and agricultural communities to prepare for the coming changes and understand what the future holds.
Hello everyone and welcome to Climate Australia. I'm your host Lee Constable, and I'd like to start by acknowledging the traditional owners of the land on which I am broadcasting to you from, wherever you are around Australia and the world. So I'd like to acknowledge the elders past and present of the Ngingini people and the Turrbal and Yugara people, and pay my respects to their elders past and present, as well as acknowledge their ongoing relationship with land, sea and sky. And I'd also like to introduce you to our guest today. I'll start by telling you the topic of today might have piqued your interest. Is climate to blame? It might sound a bit clickbaity, but it actually goes to this broader topic today, which is about understanding attribution and future risk in climate crisis. So joining me today, I'm going to have 3 researchers from the ARC Centre of Excellence for Climate Extremes. So I'll introduce them one by one, starting with Professor Lisa Alexander. So let me tell you a little bit about Professor Lisa Alexander while she's on screen. She is a Chief Investigator at the ARC Centre of Excellence for Climate Extremes. Lisa is an IPCC lead author and contributed to the 2012 Special Report on Extremes. Her primary area of research is to understand the variability and driving mechanisms of climate extremes, and of particular significance is her ongoing work assessing global changes in extreme temperature and rainfall. Welcome, Lisa. Great to have you here. And my next guest that I'll introduce is Professor Julie R. Blaster, who's another Chief Investigator at the Centre of Excellence for Climate Extremes. I'll bring her up on screen right now and tell you a little bit about her. So Julie is an award-winning climate scientist who uses climate models to investigate mechanisms of recent and future climate change, with a focus on shifts in the Southern Hemisphere atmospheric circulation, tropical variability, and climate extremes. Welcome, Julie.
Thanks, Lee. Great to be here.
And our third, last but not least, guest today is Gab Abramowitz. So Gab, let me tell you a little bit about him. He's an Associate Professor and Chief Investigator at the Centre of Excellence for Climate Extremes. His primary area of research is in evaluating models in climate science, ecology and hydrology. His research examines whether independent climate models provide independent projections of future climates and where biases may occur. And he leads the development of a tool that provides model evaluation and dataset evaluation tools. So welcome, Gab, and welcome everyone. It's great to have you all here. So let's start with the 101. Lisa, I was wondering if you could tell us attribution and risk. What does that mean? I know you've got this research program around those things. Let's start with the basics.
Okay, so for this particular research program, attribution, if I can say it, is really about understanding the processes behind particular extreme events, let's say like heat waves or storms. And what do I mean by a process? Well, let's take the heat waves as an example. Well, heat waves are influenced by, the position of weather systems, high and low pressures, and where warm and cold air are coming from, and how these things interplay and interact with each other. And on top of that, how dry or how wet soils might be, they can also exacerbate or dampen how severe a heat wave might be, for example. And on top of that, what's happening in other parts of the country or over the ocean, that can also have an influence on how heat waves play out, so and how all of these things interact. So it's quite a complex problem. But on top of that, then we also want to understand the role that humans might play in enhancing or exacerbating heat waves, for example, through increases in greenhouse gases. And basically all of these things come together and interact with each other to create a complex picture of how extremes might play out, and how they, how severe or how intense or how long they last. And that then, I guess, takes us to the risk part of the program, which is really trying to understand, given all of this complexity, how these types of events might change in the future. And for that, we need some really advanced modeling and data processing techniques. So it's also worth noting, I guess, that, I gave heat waves as an example. Some things like temperatures we're better at than others and are easier for us to do, whereas other things like storms or heavy rainfall, these are harder, more complex things for us to understand.
So does that mean, so you've got attribution, which is what caused or exacerbated this, and you've got risk, which is what is the risk of this happening in the future at various different, levels of resolution into the future that you can see.
Yeah,
so
and based on
different
scenarios, for what might happen in the future. Yeah.
Mm-hmm. And based on that, you're saying we're better at some things than others. Does that mean we're better at the attribution side or the risk side, or do they both always go hand in hand?
Well, I guess it goes hand in hand somewhat, because again, if I take the temperature example, we observe temperature very well. So we've got thousands of observing stations around the world, which are run by the National Meteorological Services. And some of these stations we've had going back hundreds of years. On top of that, we've observed temperature from space, from satellites, for several decades. And importantly, we have what we call proxy records, and these are things like ice cores or tree rings or corals, from which we can estimate temperatures going back, hundreds of thousands of years. So we're very good at observing some of these things. And also with temperature, it's one of the parts of, let's say, a weather variable that is very consistent across space. And if I can maybe give an example of that, if I use the Sydney example, if you've got a heat wave in Bondi, you're likely to have a heat wave in Parramatta out in the western suburbs. But similarly, if you've got a very severe storm in Bondi, it might not be raining in the western suburbs. So these things sort of, we come up with this complex picture, so we understand a lot more about what drives temperatures. We're good at observing it, and we can model it really well. Whereas the other things that are more complicated and maybe aren't as spatially consistent are actually a lot harder processes for us to understand. And then that also means that into the future,
they're harder for us to estimate the risk as well.
Yeah, I just want to acknowledge the chat. We've got Ken saying, hey everyone. Doug saying, g'day Lee from Tucson, Arizona, great topic. For him says, hello. And Ken asked the question, which side is harder to model attribution or risk? And then said, question asked. So yeah, it is a tangled web you weave, which brings me to Julie. So Lisa just mentioned, ice cores and different things. You're actually looking at kind of the recent past as well as trying to look further back than the recent past. So how do observations kind of feed into your research of attribution and risk?
Yeah, thanks, Lee. I guess I wanted to just quickly pick up on one of Lisa's comments and your question about attribution and risk, and how I guess our understanding when we're looking at the recent past can really help us feed into future projections and really constrain sort of those projections. And so if we better understand what's caused changes or how climate change, human influences have impacted our climate, and particularly extremes in the recent past, then that can help us understand how that might change in the future. So they're really, I guess, tied together. And that's why in this research program, we've got them together as well. Yeah, so in terms of observations, as Lisa said, some variables we have really long records for, and those proxy records are really important at understanding how things like temperatures and also droughts have changed. In Australia, we're a very variable climate here, so it's important to have those long records. But attribution also requires not only these long records, but also a really good understanding of how our climate system works. So a lot of research has gone into that over many years. And also the climate models are really important for, I guess, helping us assess the different influences. So how much of this is just internal variability in the climate system, and how much has humans really changed that climate variability and had an influence. Yeah.
So what are you looking at as far as recent past? Is that just recorded data from the last, 100 years? Is that how recent past is? Or does it go further back than that?
Yeah, some of these proxies can go a long way back. For example, with CO2, we have records for, I think, 650,000 years from these ice cores. So that's a really long record. Corals and tree rings have, up to, I think, 1,000 years. Others may jump in if I'm not quite correct on this. And so in our program, in the Centre of Excellence for Climate Extremes, we have people looking at those paleo records. But we really also focused on, for extremes, where we have really good data, which is, as Lisa said, more from our observational networks, which we have good records from the last 100 years from those, and then satellites for the last 40 to 50 years.
Mm-hmm.
Yeah, and so some of the things that, say, we're interested in this program is looking at going beyond the global temperatures. And so we know IPCC has been really good at using attribution studies and climate models to say that most of the observed warming since the mid-20th century is the dominant cause of that is human influence. But now we're really interested in asking similar questions for regional climate change and extreme events. And that presents some challenges, but also opportunities, because that brings it back to where we live. It's not this abstract kind of global temperature, but it's bringing it back to how has climate change influenced temperatures in Australia, or extreme weather in Melbourne, where I live, for example. And we saw a big example of extreme weather last week in that.
Yeah, and so when we're talking about extremes, do extremes look the same or different when you're looking over the record, or how have extremes been changing over the records?
Yeah, so certainly with temperature, we get a really strong signal. So we're getting many more hot extremes being broken. So records being broken in terms of temperatures than we are cold extremes. And so that's a signal that we understand due to climate change. We should get more of these hot days happening more frequently and less cold days. With rainfall, Lisa has done a lot of work on this in the observations, and there are some signals, but it's as she said, it's harder to observe. But we do expect that the atmosphere in a warmer world does hold more moisture. So there's certain understanding that we have that goes into all of our research and also into our climate models that we use to do these attribution studies.
Yeah, and I guess this brings us to, we're talking about the past, but we have to kind of understand these links between things in the past and the recent past and present to know how well we can predict, or not predict, but forecast future risks. So Gab, can you give us an example of why this is important for our ability to understand risk as it applies to the future, like in agriculture, for instance? I know you're interested in.
Sure. So obviously, the observational streams that Lisa and Jill have been talking about are really important for getting a sense of what's happened, but also really important for constraining climate models and understanding how well they're working and how useful they are for predicting the kinds of things we're interested in. So one of the things in the area of this program that I'm working in is essentially making better use of climate model projections, and it's sort of one of the themes that we're really looking at. So I don't know whether I should go into this, but just in case people aren't that familiar, but climate models are very complicated computer programs. They can run into millions of lines of code. They run on supercomputers, and they simulate things like energy cycles, water cycles, carbon cycles, nutrient cycles, dynamics of the atmosphere and the ocean and the land surface and ice. And they do this by essentially breaking up the globe into this 3-dimensional or 4-dimensional, including time, grid, and simulating all these things discretely in each sort of grid cell, in each grid point. And they're really useful because they can allow us to predict future change, which is obviously quite useful. And there are some caveats, because a climate model, no matter how complicated, is much more simple in the real world. But they also let us try to get an understanding of what are the causes for the changes that we've seen, and what are the causes for the changes that are projected in the models. And you can do that because you can play around with some of the numbers in a climate model. You can say, what if we had emitted way more greenhouse gases or way less, and what kind of a difference would we see? And assessing how meaningful that is basically about assessing how well climate models agree with observations, the kind of thing that Lisa and Julie have been talking about. And if we're confident in a particular sort of set of process representations in a model, we'd be more confident about the kinds of changes we see in it. So there are obviously lots of different climate models from different groups around the world. So every largish climate group around the world will maintain a climate model, and this could be as small as tens of scientists, but typically hundreds of scientists maintaining a climate model. And like I said, climate models are, despite the fact that they're massively complex and run on supercomputers, they're still very simple compared to the real world. So everybody makes slightly different assumptions about what goes into a climate model and how they want to represent the world, right?
Yeah.
So one of the key questions that we're interested in here is all of these simulations are slightly different from these different groups, and how do we best utilize the information that they can give us to make better predictions for things like agriculture? This is a long way to get into your question, Lee, I know, but some background is probably quite important here.
Yeah, for sure.
So one of the things, for example, that we want to look at is should we average these models, which is a really common thing to do for a particular thing we might be interested in? Should we give them weights? Should we weight one model because it seems to perform better than another?
And these models, I'm just trying to understand the reason why there are so many models for same or similar things. Is it because these different groups of scientists are trying to find what model works best for their geographical location, or is it just because there's debate about what the best model is for forecasting?
It's typically both of those things. So you can imagine, as is the case in Australia, that if we run a climate model run and developed by our own research institutes, we want that to perform really well for the applications that we're interested in, which is in Australia. And the same is true for every other country. So that's definitely part of it. But also they're all global, and they have different groups of scientists working with each other. And so they make different decisions about how they treat convection in the atmosphere, or how they treat vegetation on the ground, or a huge range of different things. So they all come up with slightly different answers, and sort of interpreting that and pulling out the best information we can for particular problems we're interested in is one of the things that we want to do. Specifically for extreme events. So that could be in an agricultural context, or it could be for, like Lisa was saying, heat waves or extreme precipitation or drought, something like that. But really working out how we can better pull out the information from the existing climate models to get at sort of local scale information. So that's one part.
If I can jump, sorry, if I can just jump in here. Another reason there's so many is that we're looking at future climate change, right? And so we can't actually assess how skillful those models are, because we haven't got there yet. So it's really difficult in some ways to say which one is the best model.
Yeah, and I suppose it also becomes difficult because we can all imagine different futures. We have the future scenario that everyone, goes to zero by 2030, and I'm sure we can all imagine scenarios where that doesn't happen and nothing changes and everything's exactly as it is today when it comes to emissions. And so in that instance, you're having to give several different scenarios.
So there are kind of different to that, right? So all of these climate models, there's this whole kind of farm of climate models that are out there, and when they get together once every few years and run these comparison exercises called CMIP, Coupled Model Intercomparison Project, they all will run for different emission scenarios to try and get a sense of what's the possible spread of behaviour for a low emission scenario, what's the possible spread of behaviour for a medium emission scenario or a high emission scenario. And a lot of work goes into defining those emission scenarios, because they involve not just economics and sort of social science about how economies are going to work, how they're going to knowledge share, and what the resulting greenhouse gas concentrations will be in terms of warming. And that then gets fed off to the climate modelling groups to go and run for different scenarios. But the idea of having even for a given scenario, the idea of having multiple different models has been a long-standing thing in science. This idea of multiple working hypotheses. If you really want to get at a problem, usually the best answer comes from lots of people coming at it from different angles, and then trying to synthesize the end result.
And of course, the only experiment we can run is the one that we're running live, and we can't really run that again and again in the same sense of a lab-based science. Perhaps what you were just talking about might touch on what Ken's asked in the Simpatico chat. It seems like global impacts of human influence would almost be easier. I don't know if he means easier to factor in than local impacts scientifically, is in inverted commas. However, at least older locals can and do observe dramatic changes in their local climate over a lifetime, which is harder / easier to get public buy-in on. By public buy-in, I'm not sure if he means people trusting the model.
So, Lisa, I know you've given a couple of slides before about people, newspaper reports about people who've lived in areas and how accurate remembered records are, and how difficult that is. About that, I can talk about the modelling side.
Yeah, so it can be so. So I think in terms of buy-in, I take the point. Actually, in terms of scientifically, it is actually easier for us to get a global picture because our models are built globally, and the results, when we get the results out, we're pretty, they're pretty robust in terms of our global outcomes. But in terms of where people live, they don't really care about what's happening globally. They want to know, will I have more heat waves, more extreme storms, more floods in my area?
Should I sow this crop now, or should I harvest it now, for that matter?
Exactly. So, in terms of impacts, absolutely, it's more important locally, and that gives us like a real problem, because the robustness of the science is at one level, and people really want to know what's happening at a regional or a very local level. And that's kind of where our research program comes in, because we want to try and, bring these things together and try and understand, not just what's happening at a global level, but, how that will impact people at a regional level. And what Gab's talking about is, there are a lot of historical records. People over many hundreds of years have actually written, it's called documentary evidence, and they have written this stuff down for, it was excessively hot or wet today or whatever. And we can take those, but actually we have to take them with a little bit of a pinch of salt, as Gab said, because sometimes people's memory, if things aren't written down, is not as good as they think it might be.
Even in the Black Summer bushfires, you could hear someone's account where they were like, "Oh, we've always had fire. I can remember bad fires."
Yeah, and they probably did remember a bad fire, but they can't sort of quantitatively determine whether it was the same as the Black Saturday fire.
Lisa, wasn't there an instance in the early colony in Sydney where they essentially said, "We've never seen anything like this rainfall event. It was absolutely out of control." Yeah, everything was flooding, and some 5 years earlier they documented a much heavier.
Yeah, I think 2 years. The oldest resident in Sydney had said, "We've never seen these rains before." And when you look at the actual record, 2 years earlier there was an event of that size. So we have to be a little bit careful about those kinds of things. But in saying that, local knowledge is actually very, very important as well. So it's not to be disregarded. It's also important, but we need to put it within the context of all of the pieces of information that we have.
Yeah, and I suppose the other thing is, in Australia we have perhaps an even longer human, storytelling record of different events through Indigenous knowledge systems. How does that factor into when you're actually looking at records for Australia?
Well, it certainly is a factor. I mean, we can't deny that knowledge, because it's something that's really important, and it's got a very, very long history. And I think when we do acknowledge that these sorts of information, on top of all our instruments and our satellites and whatever else, documentary evidence, written and oral histories, all have to come together for us to understand the sort of rich climate history that we have. So absolutely, it's something that
I think we will over time get better at it. I don't think we're particularly good at it now. Yeah. But even in history, documented evidence in different ways is only making, from Aboriginal communities, is only really making a start in the history records.
Yeah, and often it's the fact that there's things that you can see in multiple different types of evidence, whether it's oral history and then, through looking at coral and through looking at tree rings. And then you go, well, there's a strong suite of evidence for this type of climate at this time, which is really cool. Well, we're almost at the end of our half hour already. We do have some questions in the chat. So I think what we might do is I might pass it around to all of you for any takeaways that you would hope that people watching, when they're thinking about attribution and risk and why they should even care, and your big questions that you're trying to answer. So I'll pass it around to each of you one by one to give us a little takeaway for people who might want to know more or want to have something they can think about as they go about their lives in looking into risk every day in terms of climate. We'll start with you, Lisa.
Yeah, so I guess a takeaway for me is what happens globally has impacts locally. And really, I want people to take away the message that, we want to be able to give people the information about how risks might affect climate risks might affect them in the future, but also to note how complicated the picture is, and that it's not something that we can very easily do, but it's something that we're trying to do.
Absolutely. It's a good reminder that, you know, people might get a bit annoyed when something that they said was going to happen doesn't happen, but you can see when there are so many different things that go into even making any form of forecast of risk and attribution that you know, we just have to take the best of what we can and try to improve it, don't we? Yeah. Julie, over to you.
Yeah, I think for me it's that these multiple lines of evidence are really important in attributing and understanding climate change and the future risk, and yeah, all these observational records that we've talked about, our understanding of the climate system, and importantly our climate models, and having that Australian knowledge for understanding things that are specific to our region. So, for example, in the Southern Hemisphere, we have a unique set of influences because we've also got the Antarctic ozone hole, and so that's affected our climate, and we expect it to affect things going forward into the future. And so having that local knowledge is really important too, and that we can, as Lisa said, put all of our knowledge together and try and rise to the challenge of getting this information that we know people need and want. So trying to improve that as we can.
Yeah, and it's great to see that there is local research happening through the Centre of Excellence on this, given how important local information and local models are in all of this. And Gab, what's your takeaway for everyone?
I think I'll stay on the same theme that Lisa and Julie did, and just say that one thing that I didn't quite mention about where we're going with this other half of the attribution and risk program is really trying to bridge these scales. So one thing I didn't mention about the climate models is because they are so coarse resolution, there's not a whole lot of supercomputing power, not enough supercomputing power out there to get to the resolutions that everyone wants, and there are uncertainties, obviously. We're trying to use some new techniques to try and bridge that scale to get more local scale information, involving something called machine learning that we don't need to go into here, but it's sort of trying to better use the different observational streams that we have, that we know are relevant and we haven't really known how to utilize them necessarily so far, to try and bridge that spatial scale. So as both Lisa and Julie said, the scale mismatch one is a huge problem for, or something to be resolved for climate projection, and it's something that we're actively working on.
Absolutely. Well, thank you all so much. And one takeaway from me is that all of this is important because this research needs to not only, stay in the publications and the climate science community, but of course is so important when it comes to our everyday lives, our financial well-being, our health, our environmental well-being, as well as just figuring out, business decisions and family decisions. So thank you so much for introducing us to attribution and risk and how it's relevant to all of the big questions that you're working on. What we're going to do now is we're going to just roll some credits, but we do have some questions that have come through that I haven't been able to pose to everyone. So if you've asked a question or if you've got one, please type it in the chat wherever you might be watching. We will try to get to your question. And we'll come back after that and have a bit more of a chat and go through some of these burning questions that people have. Thank you all so much.
Thanks, Liz.
Megan will let us know when we're back. But the questions are in the chat there if you want to look. Alvin's asked some good ones.
Okay.
Awesome, we're back. So to get to a few of the questions that we had, Jason asked, he first said, hi, all smiley face. Question, it sounds like you're bringing together data from so many sources. Are there any issues with non-standard formats or unit conversions, i.e. affecting accuracy or usability, or is it just a matter of effort to process?
All of the above. Yes, there are major, especially with the really old historical data, and even with some of the more modern data, there are always issues with data formats, units that we have to uncover. Sometimes we find things like, digits transposed, maximum and minimum temperatures in the wrong columns. And, so we just need to, over time, you basically find all of these problems, but it is actually a massive effort to bring all of these different formats together. And actually, 95% of the work in, I would say, the observational field is just bringing all of these sources together and cleaning them up and getting them ready to analyze.
I was once talking to a climate scientist who said that there was an instance where a Northern Hemisphere set of data had the seasons written down as attributing to different things instead of the months, and therefore, that was a confusion because obviously the seasons are opposite the different hemispheres, and dare I say, Northern Hemisphere people are more likely to forget that.
Yes, they do.
There's examples where some of the observations from ships, I think, were put in like 180 degrees longitude out of place. And so instead of being over the South Pacific, they were over the South Indian Ocean. So there's things like that can go wrong. But I think it's a huge effort. And mostly as climate modelers, we just get these nice cleaned up data sets that we can use to compare to our models. But the observational work is really important and challenging.
Yeah, and I bet there's been a lot of work to try and get people on the same page, but then there's probably a few different main pages that people like to be on, competing models, competing ideas of which columns are used for what. And we've got another question here. Can the climate models tell us how impacts on infrastructure and society will change in the future?
I can have a go at that. Look, I think that is, again, probably a scale issue. If it's depending on the type of extreme, probably for things like heat extremes, we have a better idea of the scale in which they're going to impact, and we are more confident in the processes that lead to them. So we have a pretty good idea that they're going to be more of a problem. And so if the particular kind of infrastructure you're interested in is going to be affected by heat extremes, then there may be some exceptions, and some places on the Earth are actually cooling, but on the whole, it's likely to be an issue. But as for a particular location versus a different location, particularly if it's an extreme that is harder to predict, like heavy rainfall or storms or hail or something like that, then it's a lot tougher. And you really need to know something, have a good observational record. And one of the real difficulties with extremes is that with extreme events, there aren't very many of them. So to ascertain whether they're changing can be quite hard unless you've got really good observations. So
that's true. They are extreme because they are outliers to a certain extent.
Right. So we tend to know more about them in places where observations have been going for a long time.
Yeah, I wanted to ask more about, it keeps coming up about how we're better at some things than others. Temperature, for instance, better at than rainfall. Is that because it's harder to accurately, I guess, see the historical record of rainfall versus the historical record of temperature, and therefore that makes some models stronger than others? Or is it because even now, based on our very, week to week forecasting, that's harder than temperature too?
I think,
do you want me to answer that? Or do you want to go?
I'm happy to go, and you can chime in, Lisa. But yeah, I think partly it's just the physics of the problem in that temperatures are going up everywhere pretty much, and so it's easier that we expect that to happen as a response to climate change, whereas rainfall, in terms of our regional change, is very dependent on our circulation, so our weather systems coming through, and where the big storm tracks are, and those are less constrained in our models. Our models get different answers for how much those weather systems, say over the Southern Ocean, are going to move poleward, is what we're expecting. But the models get different answers for what that's going to do, and so it's a much more complicated physical problem. But then, yeah, Lisa and Gab can chime in as well.
Yeah, and it's also more complicated from an observational perspective as well. So so we can, as I said, really observe temperature really well. It's consistent over space. We've got lots of records. With rainfall, it's much patchier. We're only sort of sampling a small area of space, and even when we do take our observations from space, for example, so we can estimate rainfall from satellites, but the satellites all give us very different responses as to what the actual rainfall is when we sort of intercompare the data sets. So it's a problem both of observation and of process understanding and of modeling. I think all of those things.
I also don't think it's that surprising. I mean, if you think about human-induced warming as really just less heat escaping from the system, but it's warming. Temperature is going to be affected. How does that affect rain? Well, that's going to affect the amount of water vapor in the air. Well, that might affect clouds, and they reflect radiation. It can just go a whole lot of different ways, and they're more local scale processes.
Yeah. So temperatures like the
back of an envelope kind of way, you can see why it's harder.
Yeah, because temperature is like the primary thing that changes, and then everything else domino effects as a result of that.
And there are local effects, as Julie was saying. What are the synoptic patterns that tend to dominate in an area? Are they going to change as a result of more energy in the system? It's a much harder.
And I think anyone I was just going to say, I think anyone with a rain gauge at home could probably tell you that how variable rainfall is when you look at the weather station versus you. And even like growing up on a farm, I felt like I was more comfortable with the variability and patchiness of rain than perhaps other people who hadn't had a rain gauge on their fridge all year, a rain, data sheet on the fridge all year round, because, you'd have this observation right here in this home paddock, but then you'd hear people going, oh yes, the back paddock didn't get any rain and the paddock over there got heaps. And, whereas maybe when it was temperature, the whole farm probably got around the same temperature at
the whole region.
At that time. Yeah, or the whole region. Yeah. We've got one more question here. High risk climate phenomena like bushfires and droughts have multiple causes. So how much more difficult is it to understand how they'll change in the future with climate change? And is there anything we can say about how these events may change in the future? It's a big one.
It is.
I can start just by saying the way we attack those kinds of problems is to look at what we think the causes are, the primary causes, and maybe even try and rank them, and then have a look at how well we can predict these things in terms of comparing with the observational record and what kind of observational records we have of them, and where we think we have skill in a climate model or some kind of modelling system framework to do that. Look at what the changes that it suggests are. So
because I guess the causes are things like leaf litter and fuel on the ground, but then also the moisture content of that fuel, and that's so dependent on policy and things like that, as well as weather events making it possible to burn off or not and reduce load.
And dryness is probably the biggest of those. I mean, if you have a really long dry spell, you don't need a whole lot of stuff to burn before it burns really well.
Yeah, because you can make and I guess you can say there'll be the conditions in which fire, if it happens, will take off in a big way. But you can't really ever say whether that ignition will happen for sure. Yeah.
It's all about trying to work out what's the current sort of distribution of behaviour, what's the spread of what's the likelihood of a particular event. I don't think anyone's in the game would any of us would say we could predict a particular event. It would be about saying, you know, what is the kind of range of behaviour, what's normal historically, and can we see any reason why that would change?
Yeah, and we look at changes in fire weather. So the fuel is really critical, and then if you have a particular type of weather event happen, you know, it tends to be these really strong fronts that come through when we get this bushfires, and so definitely part of our research is to look at those really extreme sort of weather events and try and understand how well we can model them and how they might have changed in the past. And that gives us some insights into how they might change in the future.
Yeah, I mean, this is why you have this whole research program, because there are so many known unknowns to research, aren't there? Yeah, so this is fascinating, and I think we could ask you questions all day, every day, but we have come to the end of our time together. Thanks so much for hanging out for a little bit afterwards to answer some more questions. I really appreciate all your time, and I look forward to seeing the work that comes out of the program in the future.
Great, thanks, Lee.
Thank you, Lee.
Thanks for having us.
Thanks very much. And thanks to everyone for watching, whether you're on Simpatico or on YouTube or on Facebook. We'll be back. This is only the first of a whole series of episodes we'll be doing with researchers from the ARC Centre of Excellence for Climate Extremes. So please be sure to keep an eye out for our future episodes. And if you haven't already, sign up to Simpatico TV to join in the conversation. Thanks, everyone, and goodbye.